The recording has been started. First of all, a disclaimer. AP is a trademark registered by the College Board, which is not affiliated with and does not endorse this resource, nor is the 5.5 team. Let's start the session by a brief introduction about 5.5. This review session was prepared by reading as part of 5.5. Led by Lance, 5.5 is a volunteer student run initiative with more than 70 volunteers and more than 10,000 combined volunteer hours that seeks to provide resources for students taking AP courses. And please consider checking out our website, 55.org, if you want additional AP resources and practice exams. If you'd like to contribute to 55 by creating resources, hosting lectures, or promoting this project, please check out the application document for information. And we will review applications on a rolling basis. I'm going to send a link of the application document here, just in case anyone to look at it. And for some expectations, you are allowed to ask any questions at any time. But since I expected there might be a lot of messages here, I just want to use the question column at the start of question so I can see it better. And I react with eyes emoji and answer questions as soon as possible. Secondly, you should participate activities in the chat. It will reinforce your understanding, and also please use follow types for answers as well. Finally, please fill out the 5.5 lecture feedback form at the end of the session. It really helps me to improve, and I can host better lectures for you. I think I'm going to double check. Can you all see the screen? Now I will send the screens in the slideshow in the chat. And this is our table of contents. First of all, we'll do a bit of pre-calculus review. Then we'll do limits. We need to define estimate, determine it. And then we'll go through the squeeze theorem. Then we'll go to continuity. We need to define continuity and their types. And then the intermediate value theorem. And then we'll play a Kahoot game, and a list of additional resources will also be provided. And then we'll have a question answer at the back. I will try to share the screen. Yes, it's a very quick review of factoring and also the behavior of polynomial rational functions, which are often quite useful to determine limits. Okay, some factoring practice. I think you can do it within 2 minutes. The last two might be a bit challenging if you forget how to use the factor theorem. Happy to see your answers. Yes, I'm recording this session. I send the recording in the lecture schedule sheet after the session. You can send a screenshot of the factor statement in case you need a review of pre-calculus. And I will go over the answers in around 1 to 2 minutes. Feel free to send the answers in the chat though. Yes, I will do that. I will go over the problems in 1 minute. Feel free to send the answers of the question on the screen. Thank you for your answers. I think I'm going to go over them now. First one, we have a difference of squares because it's x squared minus 1 squared. So we can apply the difference of squares formula to get x plus 1 and x minus 1. This is how we factor the first one. For the second one, it's different, and it doesn't seem like factorable at first. But it looks like y squared minus 2y plus 1 is kind of uniform. In this case, y would be equal to sine squared of x. So we can apply substitution. You can still factor without substitution, but apply substitution will make this a bit easier to see. So the factorization would be sine squared of x minus. We can do one step further because we know that sine squared x plus cosine squared x equals to 1. We can also rewrite it as cosine squared in the inside bracket. For the third one, I see some good answers in the chat, and it is y to the power 3 plus 1 to the power 3. The sum of cubes, which is in this form. And for the last one, it is a quite challenging factoring problem because we need to test for example when x equals to 1. This polynomial 0. This means that x minus 1 is a root of this. So I can do synthetic division. to get it equals to x minus 1 and x squared minus 5x plus 6. And then we can factor this. It'll be x minus 6 and x plus 1 as well. And don't worry if you don't know the last two, because they are quite challenging, and I don't think they will appear too much on the exam. After some factoring practice, we need to review the end behavior polynomials. And this actually involves limits already, and it is quite useful. The end behavior polynomial function depends on its degree and leading coefficient. So we have 4 types here. When it's odd degree and positive leading coefficient, on the right side, it will go up, and on the left side, it will go down. When the leading coefficient sign changes to negative, but it is still odd degree, then the behavior will shift completely. So it goes up on the left, but goes down on the right. For even degree and positive leading coefficient, it will go up on both sides. When the leading coefficient changes into negative, it will go down on both sides. So here are some practice problems we're taking. And what is the end behavior of y equals to negative 3x to the power 4 plus 2x squared plus 1? The end behavior would include both the when x goes to negative infinity and also infinity. Here's the type your answer in the chat. The slideshow link in case you need to access it. Slideshow link is also in the chat in case you need to access it. I think I'm going to go over this problem. This problem entirely depends on the image I sent, which is also on the slideshow. The first one, it is indeed a parabola face down. It has an even degree and also a negative leading coefficient. That means that it will go down on both sides. This is the end behavior for question 1. For question 2, we have an odd degree and we have a positive leading coefficient. That means it will go up on the right side, but go down on the left side. This is actually a quite useful way to determine the limits when x approaching infinity for the polynomial functions. By the way, please ask any question you have at any time. I will answer them. Finally, we need to go to rational functions. For rational functions, we have horizontal asymptotes and also vertical asymptotes and poles. Whether rational functions have horizontal asymptotes depending on the degrees. If the degree of numerator is less than the degree of the denominator, then we'll have y equal to 0 as a horizontal asymptote. If their degrees are the same, then the horizontal asymptote will be a over b. If the degree of numerator is bigger than the degree of denominator, then we'll have no horizontal asymptote, because the end behavior will be increasing without bound or decreasing. So this is a pattern for rational functions for horizontal asymptotes. For rational function, sometimes the denominator can be 0, and the function will be undefined at the point. However, there are two types. We can have vertical asymptotes, and we can also have pole. If I can simplify the factor in the denominator, then we will have poles. If we cannot simplify, then we will have vertical asymptotes. Of our first practice, please identify the horizontal asymptote if any of the following functions. Look at the first term of those polynomials. Please just send your answer in the chat. And you can review your notes as well. Yes, I think we have our answers now. Great job, everyone. The first one is 5 over 4, because they have the same degree. And we just need to look at the leading coefficients, 5 over 4. The second one, we see that the degree of the numerator is bigger than the degree in the denominator. So there are no horizontal asymptotes. For the third one, degree of the numerator is 3, but the degree of the denominator is 5. 3 is less than 5, so the horizontal asymptote will be y equals to 0. So we have our comparison of the degrees. So we need to find the largest degree out of all of the terms and compare them. If they're the same, then the horizontal asymptote will be 5/4, which is the quotient of leading coefficients. If the degree of numerator is bigger than the degree of the denominator, then we'll have no horizontal asymptotes. However, if the degree of the numerator is less than the degree of the denominator, then we'll have y equals to 0 as our horizontal asymptote. Finally, we have vertical asymptotes and poles. Please identify the vertical asymptotes and poles, if any of them exist, of the following functions. And as a hint, you need to factor them. You still remember how to factor them. They're actually y equals to 1 because they have the same degree. So we need to compare the coefficients of leading coefficients. And if there are no leading coefficients like this, it is assumed to be 1. So it's 1/1, which is fine. We'll see the slideshow links again. So if you cannot see the string for any reason, you can see the slideshows instead. We're on practice 2 about vertical asymptote samples. So for the first one, I'm going to go over step is the factor for those type of questions. And we will see that the numerator and denominator have a common factor x plus 1. If we cancel it out, we are left with x minus 1 only. So this means that the factor in the denominator can be simplified. And according to our notes, we will only have a whole. And it's a whole at -1. It cannot exist here. As an example, so we can try to solve out together. Similarly, we need to factor, and I hope you still remember how to factor quadratics. The top is x plus 2, x minus 1. And the bottom is x minus 3, x plus 1. I don't see any common factors here. Then we have two vertical asymptotes, x equals to 3 and x equals to -1. If they cannot be simplified, there will be vertical asymptotes. With this, let's try what would be the vertical asymptotes and holes of the third one. This is going to be a bit of a challenge. Feel free to send your answers of the third equation in chat. You may need to also factor on the first step. Yes, feel free to send your answers in the chat. What will be the vertical asymptotes and holes of the third function? First step is always to factor. We know that x squared minus 3x plus 2 can factor as x minus 1, x minus 2. So, of course, an asymptote, because there are no factors for it. To 0, this is a bit tricky, because we can simplify 1. I can delete this x, and I can also remove the exponent here. However, we still have an x in the denominator, which means that we cannot simplify this x out of the denominator. So we also have a vertical asymptote at x equals to 0, and they are both vertical asymptotes. So great job, everyone. With this, I think we're ready to move on to actual calculus. Let's define the limits first. The intuitive definition would be as x approaches a, fx approaches the same number L from both sides, and L has to be a real number. We express this as this complex expression. This indicates limits. This indicates x approaches a, and we're considering what value fx approaches. So this is a definition of limits. All familiar with limits. Send screenshots throughout the session with some extra information I can see. As x approaches a, fx approaches the same real number L from the left side or the right side. The left side will be indicated by a negative number, and the right side will be indicated by a positive number. They are called one-sided limits because they only consider limits going from one side. So this is how we define limits, and it is in the topic 1.2 of the course and exam description. This, I think we are ready to continue to the next topic about estimating limits from graphs. Well, a limit does not always exist. It does not exist if the following three conditions, any of the following three conditions are true. First condition would be the function is unbounded, like here. Here, the function goes to negative infinity and infinity, so the limit does not exist here at 0. Secondly, if the function is oscillating, like it is going between -1 and 1 at a very high speed. A limit does not exist at x equals to 0. And thirdly, if the left side limit does not equal to the right side limit, and as you can see, they're approaching two different values, then the limit does not exist. These are the three conditions. So here, what do you think is the limit as x approaches -2? Yes, it's -2 because the left side limit and the right side limit approach the same value, -2. And it does not matter whether the function is defined at -2 or not. Even if it's undefined, like in this problem, there's a hole, the limit still exists. The function value at a point does not affect the limit at all. What matters is the values approaching it. Another example, what is the limit as x approaches 2? Yes, it's 4. This one is even easier because the function is continuous. So it passes through 4. Limit also disagrees with the function value. We'll talk more about continuity later, but the limit is still 4. Here we have three problems. What is the limit as x approaches 0? And also, what is the limit as x approaches -infinity or positive infinity? Based on the graph here. Disclaimer, this might seem a bit easy for most calculuses, but the difficulty will go up later. The first answer is does not exist because, first of all, the function is unbounded. And secondly, from the left side, it is approaching -infinity, but from the right side of 0, it is approaching positive infinity. So the of the abbreviation DNE. Second and third one, function is kind of approaching the x-axis. So the limit is 0 for both teams. And this is a classic example we have discussed before. It does not exist because it is oscillating towards too many values. Graph has a crazy, almost a red rectangle here in the center. And from here, we also have seen it in the example before. So we have 5. From the right, we have 6. This is 5 and this is 6. Those still do not agree with each other. So the limit does not exist. There's another practice question. What is the limit as x approaches 0? What is the limit as x approaches -infinity? And what is the limit as x approaches positive infinity? Feel free to type your answers in the chat. When x approaches 0, both sides still approach infinity. So we can write it as infinity. You can also write it as does not exist. It is still correct. And you will get marks for writing either of them on the FRQ if we ever have a limit FRQ. This is quite similar to the previous one. When approaching negative infinity and positive infinity, it is approaching 0. So we have zeros. And I think we have enough practice, so we're going to skip straight towards estimating limits from tables. We have a similar strategy for estimating limits from graphs, because we can imagine what the graphs looks like through the table values. Here is an example here. We see that the graph is approaching a very negative value from the left side, and it is approaching a very positive value from the right side. The graph might look like something like this. Just a rough guess. And 3 is in the middle here. So the limit does not exist. Here is a quick practice problem. What's the limit as x approaches 11? And as you can see here, we have a table of values. And we go from the left side and also from the right side. So what is the limit value? Yes, you can't really tell. Still someone make a reasonable guess. No. In the chat. There could be more than one possible answer, but because I didn't give the full picture, so it might be a bit hard to determine. And it is indeed 0, because it is kind of approaching 0 from both sides. And as usual, when determining limits, you can ignore this. Because the limit is about the values approaching it, not the value that is on it, so you can remove this from the table. And this way. And 0.001 might be also a nice guess, because we don't have the full picture. But the most reasonable guess would be 0, because it seems like it's continuing to decrease to a very, very small number. So if I add a lot of lines here, or a lot of zeros, it will kind of approach 0. And calculations I'm getting estimate limits from the table values. If the question gives you a function, you can still use this method to kind of estimate what the limit would be. So you can construct the limit of values, the table values yourself. That is sometimes a good way to determine the limits. So this method is not limited to just giving you the table values. You can also construct it yourself. Yes, the function is very weird. I made it up. Finally, let's look at limit laws. This is in topic 1.5. We have a lot of limit laws, so I divide into multiple parts. The first part is about related constants. So the first two should be intuitive. don't think I need to go over them because they are so intuitive. The third one is the constant multiple rule. So I can pull the c out on the left side, out of the limit. So I'm left with a more simple function. For the second part, we have the sum law, difference law, which almost mean the same thing. I can separate this complex limit into two smaller ones and just use the same algorithm. Limits is actually pretty nice because we can't really do the product law and quotient law just like this in derivatives. Yes, it's quite similar. The product law and quotient law is also just as simple as put the operator, the same operator for the two limits. Of course, the denominator can't be zero. Yes, each limit needs to exist as well. And if it's zero, it depends on what the numerator is. If the numerator is not zero, then the answer would be just like this. Or if better, you can also sometimes it might be negative infinity or positive infinity. So you can test that using the table values. But if the numerator is also zero, we'll have a 0/0 form, which is an indeterminate form because it can take on any possible value. So we cannot just say does not exist if it is 0/0. We need to apply some sort of rules to deal with it, and we'll discuss that later. And of course, some of you might know the Hospital's rule, which is quite efficient at dealing with 0/0s. Yes, Hospital, but we're not going over that in this session because that is for application. We'll learn about some other methods aside from Hospital's rule to deal with 0/0 limits for topic 1.6. Yes, they will not be part of the limit rules, but it is quite helpful to determine limits with 0/0. So I can take the power and take the root of the limit, which is very nice. We just saw so many limit laws, but in reality, we usually don't use them very often because we usually use this result, which is limits of polynomial rational functions. All the previous limit laws that we have seen, around 10 of them, if we combine them together into one, we'll have this. So this enables us to use direct substitution. Question, would the L'Hopital's rule on the previous slide only work if a equals 0, as in limits when x approaches a? A does not have to be 0. A can be any real number or infinity or negative infinity, and the L'Hopital's rule will also work. Just for reference, I'm going to send a quick stuff about L'Hopital's rule. Just yes. These some very good ways to deal with those type of situations in the chat. So I grouped the related things together. So if you think about it, those are very related towards each other. So we have this useful result that enables us to use direct substitution into polynomial rational functions, which we should have already done this so many times. So we don't need to apply the limit rules every single time when we're dealing with limits. That is going to be very, very tedious. As usual, this denominator cannot be zero. If it is zero, we are going to find another way to determine it. I'm going to go back to the composition function theorem, which states that you can also just apply the composition functions right here. We have a requirement that fx is continuous at the limit of gx. And of course, this has to exist first. If it does not exist, then we will around to. There are some nice requirements to apply this. But define continuity later. Basically, with limits, we can do almost everything we want. We can do constant multiple, we can do sum difference, we can do product quotient, we can do power root. We can also do convolution. And we can use direct substitution as a result of all of those theorems. And with that being said, here are some quick questions to do. They mean the same thing, and we're just practicing direct substitution for them. Tomorrow we'll get you some very hard questions too, dealing with 0 over 0 stuff. You can use a smaller tag, so like this form. Awesome, man. Yes, both answers are correct. We need to direct substitution. So 2 squared plus 5 times 2 plus 2 is 16. And I hope you can add them together without even calculating. Second one, it is 8 over 4, so 2. For third one, if we want to do it, it is also direct substitution. But to save time, we're not going to go over that because we need to deal with the indeterminate form of 0 over 0. And for unit 1, we do not have L'Hopital's rules yet. Of course, you can do some with it, but we just need to explore other possible ways. Just in case the sum of the conditions of the L'Hopital's rules are not met. So we have mainly 3 ways to deal with it. The most common way is just factor, like everything here, factor. And hopefully we can cancel out some factors. So I can apply direct substitution. The second way is multiply by the conjugate. That is kind of more advanced. So we can try to multiply by the conjugate of the numerator or denominator, and hopefully we'll get something better without the denominator being 0. It's using trigonometric identities. That is also quite good. So it involves applying the trigonometric identities to change the fraction. And in the end, we will cancel common factors we're doing factoring. Then we can find limit laws. So basically, direct substitution afterwards. Here are some nice examples. Here, we can factor and cancel out the common factor to get 4. For the difference of cubes, we apply the formula directly. And then we factor it, and we see that we can cancel out this as well. So we're left with a polynomial, and then we can use direct substitution. Yes, you can use L-Hospital, of course. Honestly, we don't have L-Hospital yet. Of course, you can use it. Just use the factor theorem if you forget the difference of cubes from them. So here are some challenge for you. Evaluate the following limits. The second one is pretty interesting. I will not expose it until we get to the explanation stuff. Here's the chat. We use factoring for both of them, or you can also use some other method, such as doing some simplification first, or use L-Hospital rule. I also use another method. As I see some very nice answers in the chat. Let's going to wait for 1 minute just in case anyone else wants to try. Here's the kind of multiple ways to do the second one. But it's still very tricky. Yes, you can use, for the second one, you can do that, do the expansion, and then do factoring. That's also possible way. And let's go over them. This one, as usual, we can do factoring. And then we cancel out x minus 3. So we're left with this. The denominator is not 0 anymore, so I can do direct substitution to get 5 over 4. Also final answer. And congratulations, as you get this right. Yes, you can use L-Hospital solution. L-Hospital's rule might be, I'm not sure whether it's faster for this one. If you know how to do factoring quickly, it might be even slow. The second one, this is the first method. You expand 2 plus h to the power 3 using the binomial theorem or Pascal's triangle. It is in AP3 calculus. Or you can just remember the formula. So we can break it out just like this. This is a bit tedious though. So I can cancel out the 8, and we're left with 12h plus 6h squared plus h to the power 3. And then we see that it all involves h, so I can factor it, and I can cancel them out. And do substitution to get 12. The second way is to difference of cubes. So you can use the difference of cubes, because 8 is 2 to the power 3. This looks familiar to you. A squared a to the power 3 plus b to the power 3 has a formula. Just use the factors in last one. I hope this limit looks familiar to you. It is related to Unit 2, though, but I still want to kind of discuss it quickly. Yes, it is the first one in the list. It's actually a derivative of think about it. It's a derivative of x to the power 3 at x equals to 2. If you know how to do derivatives, it is going to be 3x squared, so 12. This is also another way. You probably want to do this way in an AP exam instead of doing limit rules. Of course, you can use L'Hopital's, but I probably don't want to do that. So the answer is 12. And nice one. I think I saw the correct answer. Here are some quick thoughts about this. Why can we cancel all the common factors? Just like we will have did here. Why can we cancel all the h's? Why can we cancel out the x plus 3? So why does the cancellation work? Because we're technically canceling out zeros. Why can limits exist when they're in the form 0 over 0? I said before that 0 over 0 is indeterminate, but if you actually put 0 divided by 0 in the calculator, you'll probably get undefined instead of indeterminate. We have some nice arguments. And just in case anyone wants to put in more thoughts. Just a disclaimer, the quotient rule only works if the denominator is non-zero. We're still quite close to the correct answer. And let's see. So we can cancel out the common factors because the limit is about the values approaching it, not what it is. Yes, that is correct because it is approaching 0, but it is not 0. So it is not 0, so we can cancel them out. And limits can exist when they're in the form of 0 over 0. I see a very nice example from the chat, x over x. It equals to 1 for all x that's not equal to 0. But still, the limit will be 0 because we care about the values approaching it. The values approaching it is 1, so the limit will be 1. And it is indeterminate because you can create 2x over 2, 2x over x. It will be equal to 2 for all x that's not equal to 0. They're both kind of 0 over 0 if you do just direct substitution. So you can take on infinitely many values because I just need to change these 2 into different values. And I will get multiple values of 0 over 0. So that is also why it is an indeterminate form. So we cannot just determine the value by just looking at 0 over 0. We need to use more ways. Thank you for discussing this in the chat. This, we're going to move on to the next topic. The squeeze theorem. Here's a kind of formal definition. We have three functions f, g, and h. They're defined for all x does not equal to a over an input open interval containing a. If f is smaller or equal to g and g is smaller or equal to h in the interval, and the limit of f and the limit of h as x approaches a is equal to the same value, where L is a real number, then the limit of g is the same number. It is quite hard to see just from definition, so I have a graph here. We have f, g, and h. F is lower than g, and g is lower than h over this interval. And as they approach 0, the green function, which is g, is getting squeezed between the function h with the black line and function f, which is the purple one. So it is getting literally squeezed into 1. That's why we have the limit here. Sin x over x equals 1. We're using a squeeze theorem just like this. But it has a name because function g is getting squeezed between function f and h. And unfortunately, we don't really apply the squeeze theorem very much, since we have L'Hospital's rule. Yes, that rule exists for only when x is in radians and x is a small value. Yes, that's a good approximation in physics. If x is a big value, then you cannot use that approximation. X has to be some small value. It is useful in simple Hartman motion. I'm not going to go over that though. Yes. Let's continue. And degrees is kind of a bit hard to use, so we are default to radians in the calculus exam. So for this one, the application of this theorem is a bit difficult because you need to prove this inequality for over an entire interval. Through a table, you can kind of see that it might be true, but to prove it, you need to do some more work. And we usually don't do proofs in calculus exam. The L'Hospital's rule instead of the squeeze theorem, which is way faster. But it is still a crucial theorem. A rigorous superproof cannot use tables. You need proofs of. Yes, this theorem is unfortunately not very important. So this is a kind of a graphical representation of FGH. So if f is smaller than g and g is smaller than h over this entire interval, and the limit of f, when you calculate that it is 0, it is 1. The limit of h, it is also 1, because h is just y equals to 1. Limit of functions h and f are both approaching 1. So the limit of g also has to approach 1. Question here, does the squeeze theorem apply even if functions don't meet at a certain point? Yes, the squeeze theorem can still apply. We only have those conditions, and it has nothing to do about whether they meet at certain point or not. Just have to this inequality to become true. Fx is smaller or equal to gx, and gx is smaller or equal to hx over an interval. And we need to prove that the limit of f and h is equal to the same real number. This means that function f and h are squeezing function g into the same real number. L. This squeeze theorem we can use an Hospital's rule anyways. Okay, here's an example for you. It depends on how you study yourself. Yes, of course. How much do you already know for calculus? You can. I think we should only need about how much percentage to get a 5. I'm not very sure. Yes, it's of course possible. Yes. But you need to put in more effort. Yes, we still have time. Year 6 is pretty close to the end because we only have applications of integration and differential equations left. Yeah, so if you haven't finished studying, please do so. Yes, and by the way, you can use the graphing calculator. I forgot to mention that. This is quite old FRQ that I found for half an hour. It's very hard to find a limit continuity FRQ. In chat, I already see some very good answers after scrolling through the chat. Of course, you can use the graphing calculator. And since we are online, we can use decimals now. If you feel that it may be faster than entering a function into the graphing calculator. Just review the answers now. Because for graphing calculator, we can see it quite quickly. So here is the graph, if you put it on decimals. When it approaches negative infinity, it's approaching 0. And when it approaches positive infinity, it's going up infinitely. So this directly means that the limit is 0 and infinity. So good job, everyone. Yes, without graphing calculator, you can kind of approximate it because the exponential function is decreasing and increasing at a much faster rate than a linear function. So we should be able to ignore the 2x in front because it cannot affect the behavior very much. Kind of intuitive stuff, but you can still use the graphing calculator to verify. So finally, continuity. For types of discontinuities, this is in AP Pre-Calculus, actually. But let's go still review them. For removal discontinuity, the limit exists, but the function value is undefined or not equal to the limit. like a hole here. We have looked at this graph before, so it is just a hole. The important thing is that the limit still exists, but the function value is undefined or not equal to limit. This limit does exist. This distinguishes it from other discontinuities. If we can't lose this view, you can add that thing. And for a jump discontinuity, the limit doesn't exist. However, the left side limit and the right side limit are different, but they still exist. They still exist. Like here, they still exist, but they just are not equal to each other. So the limit doesn't exist. For infinite discontinuity, we have vertical asymptotes. Or in other words, left side limit and right side limit is unbounded, approaching positive and negative infinity. We will look at the definition of vertical asymptotes more in the later slides. Question in the chat. I think Algebra 2 teachers, I don't think they teach truth identities too much. So you can feel free to review this slide if you need to reference it later. They contain some nice definitions. Put this in the chat, and let's go on to the next one. We can define continuity at a point. We have three conditions. The function value is defined. The limit exists. And the limit equals to the function value. The intuition is that if your pen doesn't lift passing through the point, then it's continuous. So this thing that I'm drawing right now is continuous. I didn't lift my pen. So it doesn't matter whether it's how zigzag it is. However, if you have to lift my pen at one point, then it is discontinuous at that point. This is a kind of intuitive way to determine whether it is continuous or not. To prove it, please still use the definition. You can't just write my pen doesn't need to lift on the FRQ if we have one. But for the multiple choice questions, you can use them. Please remember the three conditions. They are used later. Yeah, that's a quite useful strategy. And well, continuity over an interval, we just mean it's continuous at each point in the interval. We have the same analogy. If a pen doesn't need to lift passing through the entire interval, then it is continuous over that. And we have nice property that polynomial, rational, power, exponential, logarithmic, trigonometric, and also inverse trigonometric functions are continuous on all points in their domains. They don't have some weird discontinuities inside their domain. So I know that polynomial functions are continuous over all real numbers. Also exponential. Other functions might have some weird stuff. Yes, because we sometimes have vertical asymptotes. Yes, it's continuous on its domain, but not at the vertical asymptote. Yes. Oh, I'm sorry about that. Let me send the slides here. All the slides. You should be able to see my flower icon on the slide that I'm on. I'm on slide 41. Rational functions can have positive asymptotes, so they're not continuous at those points. But they are still continuous at all points in their domains. Very important part. Not all numbers in their domains. So all those usual functions that you know are continuous on all points in their domains. Yes, but the whole is not in their domain though. It's outside of their domain, so that's why. And if the outside their domain is of course discontinuous because the function does not even exist. So they're continuous on all points in their domain and discontinuous on all points outside their domain. This is a direct implication of this sentence. So let's go to the next one. Please identify all types of discontinuities, if any, on the following graphs. You can ignore the third one because we're kind of short on time. On what intervals are the following graphs continuous? Send a question in chat just in case. We only need to do the first two. The second one, the third one is kind of repetitive. Yes, we don't need to do the third one. We're kind of short on time. I'm concluding and have fun doing the coding problems. The answer can be written in any way you want, just as long as to demonstrate you understand the point. Then we see some very good answers here. The first one is chaotic. It is kind of oscillating. And yes, it is sign of S. I use that for that graph. Yes, the second one has an asymptote level. One vertical asymptote, one horizontal one, and 4. So I think we already have all the answers in the chat. Yes, this interval is kind of correct, except for 5. Um, 5 is not continuous, unfortunately. Although the limit is a function that's like this, so it is still not continuous. The interval will be valid if I'm asking for the interval where the limit is kind of. 5 is the inner domain, but it is discontinuous though, because it is not equal to the limit value. So to draw this function, I have to lift my pen. I can just draw it over. I have to lift my pen to the bottom and then continue drawing. So it is discontinuous at 5. Yes, that is nice. I'm just going to go over the problems now. And I think we already understand it very much. This one is still continuous. So all real numbers. Although it's oscillating like crazy, it's still continuous. I can draw it with a pen without lifting it, but it is going to take a very long time for the middle. Second one, we have more forms of discontinuity. In the chat, I see infinite discontinuity. Due to vertical asymptotes, that is correct. We also see more references to holes here at x equal to 5. So we have an infinite discontinuity at x equals 3 and a removable discontinuity or holes at x equals to 5. So the interval for the second graph will be the one in the chat. Excluding the 2 points of discontinuity, every single other point is continuous. Yes, I think Unit 8 and Unit 10 has. I'm not sure about Unit 8 though. Unit 10 should already have one. Yes, if the pinch off is, it is discontinuity. I think other 5 tutors are trying to cover up all units of calculus. Yes, this is technically AV calculus topic. But still, let's move on here. For removing discontinuities, holes can be removed by setting FA to value of limit. As we know, for holes, the limit exists, but the function value is undefined or not equal to the limit. So, if I set the function value to the limit, I can remove the hole. For example, if I set the function value here, I just put a dot here, and the function is continuous again, because it is just a straight line. So that's also why holes are called removable discontinuities, because you can remove them easily. For the second one, piecewise functions are continuous at the boundary, following the same definition. The limit from the left equals the limit from the right. In other words, the limit exists. Second property, the function value at the boundary equals the limit. This is also the same condition, but worded a bit differently. We will look at this problem later. Finally, vertical asymptotes. This is technically free calculus, so it is unbounded. Like positive infinity or negative infinity for any of the limits, then we have a vertical asymptote. Also seen this in free calculus, limits at infinity and the horizontal asymptotes. Limits at infinity indicate end behavior, just like we have discussed before. And when limits at infinity are real numbers, they are horizontal asymptotes. Just like those horizontal asymptotes. Let's see over the last few examples. Yes, to find the vertical and horizontal asymptotes, I believe there is a nice summary at the front. Here's a summary. Depends on the degree for horizontal asymptotes, and it depends on the denominator for vertical asymptotes and poles. Yes, it is the quotient of the leading coefficients if the degrees are the same. Y equal to 0 if the degree of f is less than the degree of g, and no horizontal asymptote if the degree of f is bigger than the degree of g. And for vertical asymptote depends on the denominator. If the factor in the denominator can be simplified, then we have a whole. Otherwise, we have a vertical asymptote. But the function is still always undefined when the denominator is 0. Yes, I hope to see you next time. The last topic is intermediate value theorem, which is also very intuitive. F is continuous over a closed bounded interval AB. If Z is any real number between them, then the number C satisfying F equals to Z. This means that if we have a function here that passes through those 2 points, let's call it A FA and B FB. Then, if Z is any real number between them, let's say Z, this is Y equals to Z. F is continuous over this, so I cannot lift my pen. The theorem says that we have to pass through this horizontal line, which is true if you think about it. No matter how I move my pen, if I don't lift it, I cannot just magically jump through this horizontal line. At some point, I have to cross through it to reach the next point. So that is basically what it means for intermediate value theorem. We cannot jump over the horizontal line when the function is continuous. We generally use it to prove the existence of x-intercepts of a graph. When the signs of FA and FB are different, the number C such that FC equals to 0. So nice theorem to use for proofs. To save time, I'm going to go over this FRQ instead because it is harder. A 12,000 liter tank of water is filled to capacity. At time t equals 0, water begins to drain out of tank at a rate multiplied by RT, measured in liters per hour, where R is given by the piecewise defined function. RT equals to 600 T over T plus 3 for T values bigger or equal to 0, but smaller or equal to 5. And 1000 e to the power of negative 0.2 T for T bigger than 5. So we're given a piecewise function. For just part A, you don't need to read this. For part A, is R continuous at T equals to 5? Show the work that leads to the answer. And this is a graphing calculator active problem. So we can use a graphing calculator to estimate things. But we really show your work briefly. You can review our notes if necessary, because we have mainly 2 or 3 conditions of continuity. One of them is voluntary, then we have a discontinuous function. That is exam for QL. We are on slide 49, if you have from CO2. And you can do approximation when necessary. After this, we're going to take a food. I hope it's going to be fun. Yes, I saw a very nice answer in the chat. So we can test the boundaries by substituting 5. And if we do 5, t equals 5 for the left side, and we put it into our calculator, we'll get 375. However, for this one, for the second part, do substitute t equals 5 inside here, we'll get 1,000 e to the power of -1, which is a decimal, first of all, and the value is completely different. It is still close though, like 367.9. They're not equal, of course, so it's not continuous. And this is already sufficient because it is validated one condition for continuity. A nice job. After that, we're going to play Kahoot. I will stop sharing temporarily so I can share the Kahoot screen. Send a link in the chat. I believe you need to enter kind of a pattern by clicking on this pattern, which is changing every 10 seconds. So you click on the pattern consecutively in the correct order and you will get it. Wait for a bit for more people to join. It'll be a nice practice opportunity to test the skills of limited continuity. And if you have any difficulties joining, please message me in the chat. Yeah, you're very easy phone. To test the AP calculus unit 1 limited continuity skills. We have the large QR code here. And you can also join the link in the chat. Or you can just go to code.it and enter the pin of 3952079. After joining, you'll be required to input kind of a pattern. So you need to click on the patterns in the correct order to join. I believe I'm going to wait for 1 more minute just in case any of you have some difficulties joining. If you do, please message me. I think it's better to disable the patent so we can join. I'm gonna start in 1 minute at something 50 or 20, depending on something. But as soon as possible, I'm gonna start very soon. If the clock turns 11:50 for my console, which is Pacific time, we can start. Okay, I think I need to start now. And good luck. Of course, you can still join after the code start. So quick rules. You need to choose the best answer out of all possible answers. So if limit equals to infinity, and I have both infinity and does not exist answer choices available, please choose infinity because it's a kind of a better answer. And no confidence. Let's go to the first problem. Very good job. We get it. This one is a bit tricky because we have some complex expressions here. But as we can see, the degree of the numerator is the denominator, and it is approaching negative infinity. So the behavior of the first function matters because it has a larger rate of change. So it is going down to negative infinity. This is a kind of a challenging question. Relation helps. And if anyone wants to join the company, you can still do by clicking on the link. I did not lock the game, so you can still join. The answer is 1 intuitively because they have kind of the same rate of change. Because the square root of x squared is still x. So they kind of have the same Lie coefficient, so it's a big one. If you want to prove it, you can put x plus 1 inside this thing, inside the radical, if you want to actually prove it. If you put it inside radical, we'll get x squared plus 1 over bracket x plus 1 bracket squared. And in the inside, it is approaching 1. So I can apply the root law to obtain 1, because the square root of 1 is 1. It's tricky, but convention are getting it correct. They are all discontinuities. Yes, it is false because FA exists is only one of the conditions. No, sorry. Whether FA exists does not matter at all. Sorry, I thought it's continuity. So if FA exists, then the limit may not always exist, because it is not a condition at all. The limit is only about approaching. So nice job. And polynomial functions are actually continuous over all real numbers. If you think about it, it's actually true, because you can draw any polynomial functions without lifting up. Yes, the answer is false, because like tangent is discontinuity because it has vertical asymptotes. The same applies for secant, cosecant, and cotangent. Not over all real numbers, it is in their domains, so it is actually true. In the slides, I think we have kind of discussed about it. So almost all the usual functions that I have studied are continuous over their domains, but not over all the numbers. So it's kind of a tricky workflow because it leaves the in their domain at the end. So that'll be hard to notice. But I think you still understand this. And if you want to join the Kahoot, you can still join using the game finger. And we also have the link in the chat. And when x approaches negative infinity, the exponential function e to the power x will approach 0. This is kind of a property of those functions. E to the power of 0 is 1. So if I change the limit to x towards 0, then we'll have 1 as a current. But unfortunately, the limit is approaching negative infinity. So the graph will have y equals 0 as the horizontal asymptote, which is the x-axis. So it's kind of approaching 0 instead. So and I hope you know what the natural logarithm function is, it is ln x. And a pre-calculus question, kind of. So the natural logarithm function still increases. It is an increasing function. So it goes towards positive infinity instead of negative infinity. Oh, I see a nice even split. This question is kind of a bit objective, but make a reason best guess based on this. So first of all, it approaches kind of the same number because the function values are kind of symmetric. So limit should exist, first of all. And it seems like it's approaching 13. It is getting closer and closer to it. So it is not quite 12.95 because it's just 9.9 and 10.01. But at 10, it's still approaching to 9. And as usual, you can ignore what 10 is because that is not related at all to limit value. So the answer would be 13. I put this as trick questions, trick answers. So sorry if you pick it. I think you got it. Same table as before. This question is also very tricky because I also picked the wrong answer when I did the code for myself. So, well, limit exists. It's 13 based on our first question. If the limit exists, then it cannot be jump or infinite because for jump, the limit cannot exist. And for infinite, the limit also cannot exist because it is unbounded. So the fact that the limit exists and is 13 shows that we either have removable discontinuity and no discontinuity. And in the graph, in the table here, 10 is undefined. So it cannot be continuous. Because if we draw the graph, we have to lift our pen at 10. So it is removable discontinuity instead. And we can easily remove this discontinuity by set f10 to 13. It will resolve it. So it is a removable discontinuity. And don't worry, I also got tricked myself, even though I made a problem, which is very interesting. Same table as before. Yes, you can remove it because it is literally called removable discontinuity. I kind of exposed the answer, but that's okay. Great job. Negative 12 is the correct answer because it approaches negative 12 from both sides. So if it's getting close to 0, it will getting close to negative 12. And 40 is unfortunately not the correct answer because the limit is about the values approaching it, not what it is. So to do this type of problems, please just ignore this value when you're doing estimating because limit is not in any way related to the value of g0. So it is helpful to just ignore this. So the answer is negative 12 because it's kind of approaching negative 12 from both sides. And this is the same table. This is also a very tricky one. I originally picked jump discontinuity myself, but this is removal discontinuity because the limit exists. Although it sounds like a jump, it is not. The jump discontinuity can only jump once, but here we need to jump twice. To jump to 40 and jump back. So that is still remove discontinuity because the limit exists. In the previous question, we said that the limit is -12. If the limit exists, then it has to be removal discontinuity or no discontinuity. So this is also a very tricky part of our notes. This one is tricky because I put 1 as the distraction. So if you mess up the sign, you will get the wrong answer. So I think it was a big one because of that. But for this question, we can do kind of factoring. So for top, it is x plus for 12, x plus 2 and x plus 3. That's our factoring. And for bottom, it is x plus 1, x plus 2. The top is x plus 2, x plus 3. So we both have x plus 2 and cancel them out to get x minus 3. Sorry, x plus 3 over x plus 1. So we have x plus 3 over x plus 1. Substitute -2 into this. I have 1 over -1. Jacob's next one. So, oh, I'm not getting paid at all. This is volunteer. Yes. 5 is a zero initiative. So we are not getting paid at all. But I'm still happy to see you out here. And you're welcome. So I put 1 here to trick you guys. And this thing has to seven trick 2 people. I'm sorry for that. So just be a bit more cautious when doing those. Nice. I think the graph is a bit too small. So I think I should send the image of the graph in the chat. I'm going to send a link of the graph here. The next 2 questions will all be related to this limit graph. So you can access it if you want. I'm also going to send a better image in chat. Maybe. You will see the graph on the screen, but it might be small. You can also see this graph on my screen too. So let's move on. And it is 1 because it is approaching 1 from both sides. By the way, time limit is going to be 20 seconds for the next few questions. Or 30, I can't really remember. Guys, I think we got them correct here. So it is 3 because it's approaching 3 from both sides, although it is undefined endpoint. So nice. And by the way, you can still join the Kahoot unique evening. I'm going to send a link again, just in case. And a warning that the same graph will be used for the next few questions. So feel free to take 10 seconds to look at the graph. Great, 10 seconds has passed, so let's go. Yes, same graph. Yes, it's 5 because from left side it's 5. We also have a minus sign here, and let's continue. And same graph. Yes, it doesn't like this, because the left side is different from the right side. And you can still join the Kahoot. We still have a lot of questions left. We're barely halfway through. Please join the Kahoot using the link in the chat. Or you can enter the link into Kahoot.it. But let's continue. For answers. Same graph. It is infinity because it goes up infinitely from the left side. So it is approaching infinity instead of negative infinity because it is not going down. Very nice. We have 0 because the horizontal asymptote is 0. And it's approaching 0, so very good. Same graph. Yes, it is not continuous. I think I forgot to mention overall real numbers, but it's kind of assumed if you do not specify the domain. I'm sorry about that. I should have mentioned the overall real numbers. I'll fix that next time. So it is discontinuous at multiple points. Graph. I think it's kind of a wording problem because, like, this statement is true. This function, yes, it has no vertical asymptotes. It has a horizontal window, but not vertical ones. So it's kind of English form. If you're picking false, you're saying that this function has vertical asymptotes. Yeah. I will also change the wording of this one. Kind of confusing. Sorry about that. Okay, large limit. It's infinity because, first of all, the degree is higher for numerator, so it has to be infinity. If the degree is the same, then we'll pick A over 9 instead. And feel free to review your notes, because this is not a test or something. It is better to review your notes now if you forget something than just randomly guessing. Nice. The limit actually exists because it's only a. Oh no. Kind of. You need to pick the best answer. Limits. You can technically say it does not exist because it approaches negative infinity. But I think the first slide says to pick negative infinity over does not exist if it is indeed approaching negative infinity. So when it approaches 0 from left side, it's approaching negative infinity instead, because it's going down without bound. Just to emphasize the point again, a limit only exists when it is equal to a real number. It does not exist if it is not equal to a real number, or yes. So in this case, it is approaching negative infinity, so it still does not exist. But just for the purpose of this code, pick a more specific answer over like a more general one. Just for the purpose of this code. Nice, this one does not exist at all because it is approaching negative infinity from the left and positive infinity from the right. So nice job. By the way, you can still join the code if you want. The link is always there, and you can still join. But let's continue to the next one. Points are pretty close here. We're all over 10,000. Okay, this one is also a bit tricky. So it seems like the structures work pretty well in this case. So we usually use factoring because it's a difference of squares, if you think about it. It is x squared, then squared, minus 1 squared. So it is x minus 1, x plus 1, x squared plus 1. And after you cancel out x minus 1 from both sides, you get x plus 1 and x squared plus 1. X plus 1 is 2. X squared plus 1 is also 2. So the 2 times 2, which is 4. You can also use Hospital's rule. So the denominator will change to 1 only. So we can ignore it. And the numerator will change into 4x to the power 3. And if you substitute this in, you will still get 4. And for the usage of L-Hospital's rule, you're allowed to use it, but for a challenge, you can choose not to. It depends on you. And for new people joining, you can still join the Kahoot. You can still join the Kahoot using the link in the chat. We still have around 20 questions left. The code is 3952079. You can see it in the bottom of the screen. And I also have the link in the chat for you. With all that, let's continue. Nice, we have a new person joining. Thank you all for joining. Goodbye. Well, it depends how fast you can read, actually. Kind of a lot of reading. So this one is a trick option because, yeah, it has nothing to do with the function I'm equal to A. The kind of distraction. But the red option is correct because it is one of the properties of continuity. So it must be true. This question is interesting. So limit is when you go from left and from the right. From the left side, the denominator is going to be a bit negative. However, the numerator is always positive, so we have -1 when approaching from the left. However, from the right, we'll always have 1 as our answer. So at x equals to 3, we have both -1 from the left side and 1 from the right side, which we do not want at all. So that's not exist because the limits don't agree with each other. To recap, -1 is the left side limit and 1 is the right side limit. So they don't equal to each other. So that's not like this. This is a limit we have discussed in the squeeze theorem. I give 120 seconds because in case someone wants to prove it in squeeze theorem. But it is best to memorize it because it is so important. And as a hint, the next question should be related to this. Later question. So this is kind of a remote notion. So if the degree of f is less than the degree of gx, then y equals 0 is their Hartmann asymptote. For this red option, we'll have no Hartmann asymptote. And for the blue option, we'll have the Hartmann asymptote as the quotient of leading coefficients. And the green one is obviously not true. And if you just join, you can join Kahoot using the link in the chat. We still have 16 questions left, so it'll still be a nice practice. And the questions are getting harder and harder over time. Nice, we have kind of an even split here. So if f(x) is discontinuous at x equals to a, that can mean a lot of things. The limit can still exist for a removable discontinuity. So this is kind of not a direct if-then statement. So it is false. Because if f(x) is discontinuous at x to a, the limit does not exist is one of the possibilities. We also have the other possibility. The limit can also exist. So this if-then statement doesn't work. Yes, this is a trick question again. I did not mention this is kind of an intermediate axiom, the special case of it, but I did mention that it is continuous or not. So yeah, it is false because it might not be continuous, so it can jump around. Y goes 1/x is the perfect example. It has no x-intercepts, but it can find so many pairs to make this name. Yes, 4 is the correct answer because we have 4x here instead of just x, so it cannot be 1. And to prove this thing, you can kind of put 4 in front and then put 4 in the denominator, so it cancels each other out. So we have 4 times 1, which is 4. The general strategy is that, let's say that a equals to, let's say we have sine ax over bx. So the limit of x equals 0 of sine ax over bx is a over b. That's kind of a result of those things. A faster way to do those, but you can still do it by just by manipulating the limits. Nice. This question is a bit interesting because we can't really directly tell. But we can use kind of the table method to substitute the point ourselves. When approach 3 from the right side, first of all, the numerator is definitely positive. That's for sure. However, the denominator will be slightly positive, so it's only a little bit positive. So first of all, it's positive over positive, so the answer must be a positive number, first of all. And then we need to notice that when we divide by a very small number, the result will be very huge. So if you have 1 divided by 0.01, you get 100. If you have 1 divided by 0.0001, you get 1000. So yeah, so it will approach infinity. And also you'll tell that it approaches infinity because we have vertical asymptotes at 3. So there are kind of multiple methods to deal with it. And for new people joining, you can join the Kahoot using the link in the chat. You can also join in the game pane below. Let's continue. We still have 12 questions left. Very well done. I think this is a challenging question, but we still get it all right with the time limit. So very nice. It's like infinity because it's kind of the other side, because the denominator will be a slightly negative number. So nice job. Let's move on. Solve this very fast. So it is still 1. To prove it, you need to use the standard trigonometry limit of sine x over x is approaching to 1. So I can break tangent down into sine x over cosine x. And then, so we have sine x over x times 1 over cosine x. So I can separate it kind of. So the limit will still be 1. That's the result. So it's 1 times 1 over 1, which is still 1. This is an interesting problem. So it tells us that we can manipulate the inside before doing it. It might help. So let's continue to the next problem. It's amazing how you, for all of you, finish it so fast. Very good. This is also the kind of the fast method we discussed before. So yes, so kind of the same thing here. And graph it just to make sure. So we're approaching 0. And so if we use it on graphing calculator, we can see clearly that limit is still approaching 2 over 3. It's kind of the same method of 2 over 3, the coefficients. And nice job. And of course, you can use Helmholtz as well. Oh, sorry. I forgot to unmute, sorry about that. So this one is about 2 over 3. So 2x over 3x, so it's 2 over 3. And you can also do this using Helmholtz rule if you want. But still is the kind of the same method. So let's move on to the next one. The next one, we are going to have a difficulty increase here. So this means that the difficulty is going to become increased a lot for the next questions. So as a result, we have more time. Of course, you can use L-hospital if you want. So double points. Nice. For a challenging problem like this, we still did it quite mostly, so very good job. And reasoning behind it is to still use the standard trigonometry limit, but I can manipulate tangent x first. Tangent x, I can use a trigonometry identity to show that tangent x equals to sine x over cosine x. So it's kind of like cosine x over sine x times sine x over cosine x. So they cancel each other out. So inside limit, we have 1. So 1 is our answer here. So nice job. We'll move on to the next one. And if you just joined, feel free to still. So if the link in the chat if you want to do some calculus stuff. Nice, we have some nice ones. Time is almost up. Please pick one before the timer goes out. If timer goes out, we won't get any points. Don't pick anything. We all picked 0. Yeah. So, well, so the answer is chat, yes. So this is why equals to 0. Because we're going to use, first of all, this is also a standard one, so you can memorize it. You can also use the squeeze theorem, because the function is between positive absolute value of x and negative absolute value of x. So you can prove it, but I'm not going to prove it because it's going to be a bit tedious. Yes, you can also do that. And of course, the L'Hopital's rule, which makes this question trivial. After the L'Hopital's rule, it is sine x, so 0. Sine 0 equals to 0. So there are kind of multiple methods. Memorization, multiplied by conjugate, squeeze theorem, or L'Hopital's rule. So there are 4 ways. And very nicely done. We all got it correct. So let's go to the next challenge. We have 7 consecutive correct answers. And it's all double points. So it kind of double the points. Please tell me your answers. We're getting 3 seconds back. 2, 1. Okay. So, first of all, direct substitution is possible because this is continuous. First of all, for trigonometry functions. So you can direct substitution, but yeah, if you memorize the value of sine pi over 12 and cosine pi over 12, then very nice, you can do that. However, you can use the trigonometry identity to transform it for doing this. So cosine squared x minus sine squared x equals to cosine 2x. That is a trigonometry identity. You can prove it by using the cosine angle sum identity. So cosine 2x is cosine pi over 6. And I hope you know cosine pi over 6 equal to square root 0 over 2. This is a kind of pre-calculus stuff. So yeah, the answer is the yellow one. And good job to you, the 3 of you have done. If you don't know the trigonometry identity, then it's going to be very hard. Another double points. get the correct answer. So this is multiply by the conjugate problem, because you multiply by the conjugate for the denominator, and so you can make the denominator non-zero again. So nice. Of course, you can always use Hospital's rule. We got 10 as the correct answer for this one. Next, we have 9 correct answers in a row. Let's go to the next one, which is also double points until all the way to the end. Nice. Oh, let's get the correct answer again. This one is also multiplied and conjugate. You can multiply by square root of x plus 1 plus 1, and you will get something good afterwards. So here you direct substitution. Of course, you can always use the Hospital's rule. Nice. The answer is 1. And we get that by multiplying the conjugate, because this is 0 over 0 form. And the helpful tip is, if you see radicals and it is 0 over 0, multiply by the conjugate might be your best way to do it. Of course, you can use Hospital's rule. So let's continue. I think we are a bit over time. Also nicely done. We have this because remember the factor we did at the beginning of the session. We did sine to the power 4x minus 2 sine squared x plus 1. It's a similar strategy, so it's kind of the binomial square formula. So we can convert the numerator into sine to the power 4x, because we can also use a Pythagorean identity. So after applying Pythagorean identity, we can get sine to the power 3x as a result. So sine 0 is 0. 0 to the power 3 is still 0, so 0. That's our answer. Of course, you can also use the Hausdorff's rule. It'll be tedious, though. We can still use it. Yes. So 1 minus cosine squared is sine squared. So 0. And let's go to the next question. 12, correct? So good luck on this most challenging level of all. I think most of us choose 0, but we can see it on the graph actually. So if you use graphic calculator, 0, but since we don't have calculators, we need to use a squeeze 0, and it's kind of very complicated, so that's why I give this much time. So I think we are a bit over time, so we have to move on. Don't worry if you get a low score, it is not about competition anyways. I'm difficult, which is interesting. Okay, let's finish this with some Kahoot. So here's some more resources. Let me give you a slideshow so you can navigate to the slide. So these are some resources that I use to prepare. So it might also help you. So take a look at it afterwards. And please fill out this survey. It only takes a few minutes and it helps me improve a lot. I really appreciate it and will help us improve our lectures to help you ace the lecture. So please fill it out. With more feedback, I can become a better lecturer overall. So I can help you better to get a higher score on AP thing. My pleasure to teach you all about Leibniz continuity. And first of all, sorry for being 1 hour over time. I did not imagine that. So if you have any questions, you can ask me. It would be better if you message me privately so I can get back to you about Leibniz continuity. And I'm going to stop recording, and I think it is going to be uploaded into the lecture sheet. Probably in a few minutes. It takes a while to upload them. I'm not sure. We'll see you all next time on the future calculus lectures. There are also many other cool lectures hosted by Jerry Z. Offens and the Cool Savage. So feel free to attend their lectures as well. And I hope to see you all next time if you don't have any questions. Bye, everyone. I'm going to end the recording now.